Thanks for coming to my talk. My name is Sam Anderson from the University of British Columbia, and I'll be discussing my research into regional hydrological modeling using deep convolutional recurrent neural networks by exploring a case study in Western Canada. Broadly speaking, mapping weather through to Streamflow has implications for forecasting on a range of spatial and temporal scales, can influence how we plan our water management, and allows us to gain insights into the hydrological system. Recently, long short-term memory networks have been found to be useful tools in hydrological modeling as they're designed to learn complex relationships between sequential data on a range of timescales. Notably, they've been used to outperform standard hydrological models and have demonstrated the potential for prediction at ungauged basins. As an example of their use, the input to these networks could be time series of the past year of basin averaged weather variables, which is then used to predict streamflow at a single station. The success of this approach is exciting because it highlights the usefulness of deep learning in hydrology, and many questions exist now around how else other deep learning tools can be used and what we stand to learn about both deep learning and hydrology by using them. For example, how can we explicitly incorporate spatial information into a deep learning hydrological model? And how can we interpret the model's decision-making? The work that I'll discuss today begins to address these questions by using spatially distributed weather variables as input, which feed into a convolutional recurrent network, where the output is the next day of streamflow at a host of stations throughout the region. So I have two goals for this talk. The first is centered around performance, where I'll demonstrate the effectiveness of a CNN LSTM architecture to predict streamflow at multiple stream gauge stations simultaneously. The second is about interpretability, where I'll ask, for each streamflow regime present, is the model learning to focus on physically relevant areas of the input space? To get started, I'll now get into this first goal of performance. So this region of southwestern Canada is an interesting one to study because there are several different climate and streamflow regimes present across which we can evaluate the model. So the West Coast is characterized by warm and wet winters with frequent rainfall, followed by warm and dry summers. Mainland British Columbia is characterized with cold and wet winters with the accumulation of a large snowpack, followed by warm and dry summers through which the snowpack melts. And Alberta is characterized by cold and dry winters with a smaller snowpack, but followed by wetter summers. Throughout the region, there are 226 stream gauge stations, which have daily streamflow data from 1979 through 2015, and we will use these as our target data. Broadly speaking, this dataset can be clustered into 6 streamflow regimes. First, there are the coastal stations, which are characterized by having a high flow in the winter months from those winter rains. Then there are these 3 different styles of mountain runoff driven stations throughout BC. These stations are characterized by having a late spring onset to flow and flow through the summer from a combination of snowmelt and glacier melt, and then a range of rainfall influences in summer and fall. And finally, there are these eastern and northeastern stations, which are characterized by an earlier freshet, which in many cases is as substantial as the following streamflow peak from summer rain. So the key features to learn are melt-driven runoff, which is regional in space and seasonal in time, and rain-driven runoff, which is more local in space and daily scale in time. In the interest of building a relatively simple model to achieve our goals, we choose only precipitation, maximum temperature, and minimum temperature from ERA5 reanalysis. To create the input for the model, I'll create weather images for each day using fields from ERA5 reanalysis. Each image has 3 channels, but instead of being red, green, and blue like in an RGB image, I use maximum temperature, minimum temperature, and precipitation. Then I'll create year-long weather videos with 365 frames in the video, where each frame is a weather image from the past year. Each image in this video is then passed through a convolutional neural network, here with 5 convolutional and 2 pooling layers. When each day is passed through the model, it is mapped through to a spatial feature vector. And by passing each frame through the CNN, we can create a series of 365 feature vectors. which describe the spatial features that the model has learned which are present in each of the past 365 days. So this series of spatial feature vectors is then passed through an LSTM to ultimately output Streamflow at the stations which are being predicted. So the LSTM is learning what are the temporal relationships between the spatial features which are present. To summarize this architecture, a single weather video is passed through a CNN, then an LSTM, and the output is the next day of Streamflow at each of the stations being predicted. I'll use data from 1979 through 2000 for training, then validate from 2001 through 2010, and test from 2011 through 2015. First, the model will be trained to predict Streamflow at all stations present, and this will become our bulk model, which we can then use for fine-tuning on each Streamflow regime. To fine-tune, the bulk model weights are copied and then retrained on just one of the Streamflow regimes present. Ultimately, we can create this set of 6 fine-tuned models, one for each of the Streamflow regimes that we've identified. To evaluate the similarity between observed and modeled Streamflow, I use the Nash-Sutcliffe efficiency, or NSE. It's defined as 1 minus the ratio of the variance of model errors to the variance of the observations. Here, a value of 0 is poor performance, and a value of 1 indicates perfectly matching modeled and observed Streamflow. The median NSE on the test set is 0.67, which is quite good, but there are regional differences in performance, with the best performance in mainland BC and the worst performance in the more arid eastern region. Shown on the left is NSE by cluster, with the dark left bars indicating bulk model performance and the light colors indicating fine-tuned model performance. We see that fine-tuning seems to have only minor to moderate impacts on improving model performance as evaluated by the NSE. Additionally, we see that the best performance is found in the central, southern, and northwestern stations, with NSE values often above 0.8. Here are some results for a snowmelt-dominated station in the south and a rainfall-dominated coastal station. The shaded regions show the 2 sigma interval across an ensemble of 10 models, and we do see that the model is doing reasonably well at getting both those shorter timescale fluctuations of the rainfall station and the longer seasonal scale changes of the snowmelt station. Okay, to summarize the first goal, we've used a CNN LSTM architecture to predict Streamflow at multiple stream gauge stations simultaneously across a range of climate and Streamflow regimes. However, this is not a surprising result, particularly, I don't think. We know that deep learning tools like CNNs and LSTMs excel at regression problems, especially those for which there's an underlying physical relationship between the input and output. And so I think the question shifts from asking, how well does the model perform, to why is it performing well? For each Streamflow regime, is the model learning to focus on the physically relevant areas of the input? So consider our modeling setup, where the weather video is passed through the fine-tuned model for the coastal region. Since Streamflow in this region is driven by rainfall along the coast, we would expect that the model should be mapping the weather along the west coast to Streamflow along the west coast. On the other hand, the model should care less about what's going on in the northeast area, since the weather up there is not physically driving Streamflow along the coast. So the model should not strongly map weather in the northeast area to Streamflow along the west coast. So to evaluate where the model is focusing, we'll take the following steps. First, we pass the regular weather video through the model and predict Streamflow Q. Then we add a spatial perturbation to the input weather video, here called P, which is a 2D Gaussian perturbing a relatively small portion of the input space. We pass this perturbed video through the model and compute the perturbed Streamflow Q star. Then we calculate the difference between the regular and perturbed modeled Streamflow, delta Q, which is large if the perturbation had a strong impact on the model's prediction. Finally, we define a sensitivity S, which is equal to the perturbation multiplied by delta Q and averaged over many iterations of perturbation. If the model is mapping the perturbed area through to Streamflow, then S is large in the perturbed area. And by iterating perturbations all over the input region, we can learn where in space is most used for the model's prediction. If the model is learning the underlying physics, when predicting for the coastal cluster, for example, perturbations outside of the coastal region should lead to a small delta Q, and thus S will be low there. But when the perturbation is along the coast, then delta Q should be large, and therefore S should be large there as well. And now I'll show some results. So we find exactly what we were hoping to find for this cluster. The model is highly sensitive along the West Coast region, which is where the physical processes are occurring, which are driving streamflow. And this is exciting to see. The model has automatically learned where to focus for this cluster. Then I'll divide the sensitivity into two regions, one which is nearby or within the watersheds of the cluster, and one which is not. So here, the y-axis is sensitivity, the x-axis is cluster, and the left distribution is the sensitivity outside and far from the watersheds, while the right distribution is near or within the watersheds. And we see that the sensitivity is much greater near or within the watersheds. Looking at all other clusters, it's quite interesting, and I'll walk through some of the notable results here. The central, southern, and coastal regions are generally most sensitive in the areas near and within the watersheds of the cluster. Alternatively, while the eastern and northeastern clusters, they are sensitive within the watersheds of the cluster, they also have this second sensitive area further away. And this could indicate that the model is relying on correlations across space, which are present, but they are not physically driving streamflow. Another useful metric that we can parse out of these heat maps is the area fraction, which is most sensitive. So here I define A as being the fraction of pixels which are above the half maximum sensitivity. A large A indicates that a large portion of the input area is used for prediction, while a smaller A indicates that a smaller region is used for prediction. Visualizing A for each cluster, both bulk and fine-tuned, we see some striking results. I think most notably, we see that there is a large decrease in A between the bulk and fine-tuned models. So this indicates that the process of fine-tuning has a large role in determining where the model is focusing, even if fine-tuning does not necessarily lead to a substantial increase in NSE. This means that the simulated streamflow may not substantially change from fine-tuning, but the way that the model predicts streamflow does change. So to conclude this talk, I'll note that the CNN LSTM architecture can successfully incorporate spatial information into the deep learning model. Fine-tuning by streamflow regime has a relatively small impact on NSE, but a relatively large impact on where the model is focusing. And generally speaking, the model is most sensitive in the areas which are near or within the watersheds that are being predicted. So thank you very much. Please feel free to contact me for more information on this project.